Our last talk before the break is by Yongyun Hwang, and he's going to be talking about multi-scale state space dynamics of near wall turbulence. I think this title has a record for the most hyphenated word pairs. Yes.
Okay, thanks for the introduction, and thanks for inviting me for having nice opportunity to present the work. So I've seen lots of interesting talk about roughness this morning. I'm going to change the topic. I think I will have to continue what the Johan Duguay said actually in the first day, and that Tobias Schneider and also Padrak Stanovic yesterday. Okay, so what I'm going to talk about is basically what is going to happen if you increase the Reynolds number in this approach. So let me just briefly start from the attached eddy hypothesis. I think we have seen quite a new people here, so the who don't always work on word turbulence. So let me just give you a brief description about this. So here is the typical mean velocity profile that you see. This is a Wall number location, and this is the mean velocity profile. So the typical argument is that in the new wall region, we have a viscous inner length scale. This length scale is basically the length scale coming from the shear. And therefore the eddies, that comes from the shear, which is a coherent structure scale with the viscous inner length scale. On the other hand, if you consider the outer part, you will have the big structure related to the global shear, that the length scale of which should be the height of the channel, if I consider the channel flow, for example, half height of channel. And between the conventional argument is that there is no relevant length scale, especially in the limit of the implicit limit. So therefore, the only possible length scale is distance from the wall, according to von Thalmann's argument. And then you get the nice log layer. So which means that here in the log layer, your length scale is y. So therefore, depending on where you are, you are the energy containing eddies, which means coherent structure in usual term. The size has to be dependent on the proportional to the distance from the wall. That's what Alan Townsend hypothesized many years ago, many decades ago now. So, and also he also hypothesized that those eddies may be self-similar, both and is statistical. So we managed to actually kind of provide a theoretical basis about this hypothesis, which is called attached eddy hypothesis, a few years ago in terms of energy balance. So basically, if you have a self-similar production and dissipate the transport and integral length scale, your mean velocity profile must be logarithmic. So they also, what we have found is that we managed to find actually the kind of invariant solutions which are self-similar, okay? But these are not actually these all structures do not exist all at the same domain, but they just are self-similar. These are the representing possibly individual one. And then we are not the actually only one we computed this type of solution. Initially, the Bruno Eckart, before he passed away, he computed this sort of thing for Queplo by continuing EQ7 and EQ8 of the John Gibson's solutions. And then Tobias Schneider, actually his PhD student, also computed this for a asymptotic suction boundary layer. So the picture, so when we found this, so now we can actually kind of, in a superficial sense, we can actually use this picture, okay? So each dot here, so representing, say, individual attached eddy, and then you assume that turbulence is just bumping around, so that we've seen this pinball picture, on the first day, and then so laminar flow here is the stable the solution. So that's the picture that we often use actually to justify the relevance of this type of solutions. So what we wanted to do, okay, so let us try to test this actually step by step. That's what we wanted to do. So what we tried to do first, actually, okay, so we've seen quite a few minimal flow unit talk in this morning by Daniel and the Sherbin. So we going to consider same minimum flow unit, but we are taking a bit more aggressive approach. We wanted to cut the entire part of the wall, and we only wanted to isolate this guy. We don't want to solve somewhere out there. So we come up with we started by writing the equation for turbulent channel flow. The top equation is the mean equation for channel, and the bottom is the equation for fluctuations. And the what we wanted to do, as I said, we already wanted to focus on the viscous inner unit, but we also wanted to say that the rate assume that R tau is very large. So by doing so, we removed this term, and then at the top of the simulation domain, we apply the uniform shear stress basically, and then we removed all the the top domain and to control the hierarchy of in the turbulent flow. So we then consider typical minimum flow unit box size. So here we have a 70. Okay, so we are now really restricting the domain even more in my direction, and we take this minimum flow unit, the pioneered by Javier. So we computed quite lots of solutions, actually 13 solutions here. So and then we just visualize the usual observables that we know from steps the same process. So here, these are the streaks. This is just basically box average, the streamwise velocity. This is the also rolls, and this is the energy of the uniform rolls in the streamwise directions, and then the rest is the waves that capturing the mean during motion of the streaks. So what you see here is that, as consistent with the picture that I have shown previously, we have a bunch of the upper branch solution here. So one of them here is a periodic orbit, the short periodic orbit, and turbulence is actually really seems to be bumping around, but this turbulence is actually chaotic saddle. So the edge is leaky, as we discussed, and sometimes die out here. And then when it dies out, it's actually bumping around the lower branch solution and dies out. Okay, that's what we saw from this simulation. So we are happy by far. And what we know is that those upper branch solutions do actually form the kind of ergodic subspace of the turbulence, which means actually turbulence really visit these guys and to some extent. And then so these guys may really be used to approximate the turbulence statistics or whatsoever. So now what we have done, we consider slightly aggressive case. So now what we are going to consider, so we already consider two scale minimum flow units. So we have one big structure, and then we have a smaller structure which can live two structure can live in the Newell region. So exactly the way that we have done is that we just took the exactly same model, but we roughly actually double the box size all the directions. Okay, so then we will have one big structure here, and then we have a typical Newell structure as the smallest possible structure here. So here the situation is a bit more complicated because we have a multi-scale behavior in the system. So we had to come up with different types of observable. So what we do is that we consider turbulent velocity fluctuations, and we decompose it into large scale and small scale. The larger scale, it just contains the structure, the span-wise of size is of which is just the box size in the span-wise direction. Okay, so because typically the structures in turbulent flow is elongated, so therefore this contains actually all the larger scale streaky structure, etc. So therefore this is in a reasonable way to capture the largest scale. And then small scale, we actually just use the rest. Okay. And then what we have done, we wrote down the equation for each scale. So here is PL is a projection operator to the particular scale. PS is actually projection to the small scale. PL is a projection to the large scale. Okay. So this is without decomposing the linear term in that way. What we have done is that we multiply UL to here and US here, and then we integrate it over the computational box. So this equation a bit complicated. I think it's important for me to go through. Okay, so the three equation is the TK balance, turbulent kinetic energy balance for larger scale. This is a stream-wise component, the volume component and span-wise component. And I can do the same for the small scale. Okay. So one thing that you immediately notice is that the production term only appears in the stream-wide component. Okay. So then and it is a production term. And then you can also find the intrascale nonlinear transport. Basically, you have a nonlinear transport within the given scale. So, but these are not particularly important. I'm not going to talk about a lot during my talk. But we also see interscale transport terms. So here, these terms are the same with a different sign. So this is the term where the nonlinear transport is happening during when you have a nonlinear interaction. This term is actually pressure strain transport. It's coming from the pressure. So one thing I'd like you to note that is that because of continuity, this term satisfies these features. Okay, so if you sum up all three components, they have to be exactly zero because of a continuity. And this term is the viscous diffusion transport, which is not particularly important in many cases. So I'm not going to consider this term seriously. The last term is the dissipation. So here we should have a production dissipation balance. So therefore, the production at both and small scale must be identical to the dissipation at both and small scale. So also we spent quite a long time to compute the invariant solutions. So you see that the number is now quite a lot, so, and we managed to get the 10 exact coherent state and for larger scale and 18 exact coherent state for small scale. And we also have two unstable periodic orbits, but they're not very wide periodic orbits. So this is a phase portrait that we first see. So this is an amplitude of large scale streaky motion, and this is an amplitude of large scale small scale streaky motions. And if you look at how they are scattered here, okay. So sorry, I think I should have mentioned that this is the solution trajectory of turbulent state, and then you see that they are roughly, actually, these amplitudes roughly form a bound of the turbulent state. And of course, these are the all nonlinear solutions. Actually, you cannot do superposition between the two nonlinear solutions to construct the nonlinear solution. So, but let me do this very superficial way to see what's going on. Okay, so so that's the kind of the region that we can identify from the strength of the streaks. But if you begin to check the other observable, say this is the waves at two different scales, you see that this picture is not true anymore. Okay, this is not the only observable we examined. So I would ask actually this exact coherent state for each scale, okay, really form the ergodic subspace for the multiscale turbulence. Then my answer was quite skeptical now. Not sure about this picture. So then the question is why this is happening. Okay, of course I'm not the dynamic systems actually people, so I can't answer from in terms of dynamic system viewpoint, but I'm a fluid dynamicist. I can answer what is happening in fluid dynamics. So the things that I really found is that there are some consistent scale interaction process which are lagging in all the exact coherent states. Okay, so in the exact coherent state, those are all took out, and they are actually there in a fully developed turbulent flow. So these are the four processes I discovered by studying it, but of course I don't have enough time, so I will just talk about first two. Okay, so first of all is the dissipation. So let me just, with this actual equation, let me just briefly describe what the energy cascade is in this particular system. So we have a production, say, from larger scale. I'm not going to talk about the energy cascade within the small scale. So we have a larger scale production. Then what is happening is that this larger scale production is roughly balanced with the, not balanced with this nonlinear term in the streamwise direction and this pressure strength term, okay? And this term directly goes to here, but also this is also quite large. So therefore what is happening, once this guy takes the energy from the production, it will send to the other component, okay? And then these are all come to the next scale, smaller scale, and it does the same job. And then in that way, and then this actually energy goes to the dissipation. So in that way, highly anisotropic structure become isotropic at dissipation length scale. Okay, so the pressure strain is basically making the anisotropic structure to the isotropic structure. So let me now check the then dissipation as V and W component, and these are again the same phase portrait, and these are turbulent to cloud. You see that almost every coherent state have a problem with the turbulent dissipation, except this yellow one. Yellow one is a very special one. I'm going to talk about this very end of my talk. Okay, and then consistent with the explanation I have given you, so that we have a problem with the pressure strain here. Okay, so the exact coherent state had a problem in sending energy to V and W component and dissipation. So if you really plot the dissipation, this is one of the upper branch state that we have, the larger scale upper branch state, and this is the dissipation contour here. This is larger scale coherent state. You see that dissipation is actually quasi 2D in the sense that these are just elongated, fairly flat, like this. On the other end, if you look at the dissipation of the turbulence, it's fairly isotropic. So then where this comes from? So let me write down the equation for U. Okay, this is a pool velocity fluctuation. So pool velocity, and capital U is the mean, and I'm going to decompose the fluctuation with the x-average, streamwise average fluctuation, and the rest. Then I will have this equation for the streamwise velocity fluctuation here, and this is basically 2D Navier-Stokes. But this equation is known to be globally stable at all the Reynolds number. It will never generate non-trivial solution if you go to high Reynolds number. Therefore, only possible way to derive some non-trivial solution is through this term. Okay, and also this term contains the production term, but this is elongated equation for the streamwise average velocity fluctuation. This describes basically the lift-up effect that generates the streaks. And the rest of the equation is this, okay? And here we have another production term here. This is typically known to generate the streak instability, mindering motion of the streaks. Okay, so this is the term that you have. And the exact coherent state means actually these actually process exactly balance to each other. Okay, so this equation can generate leads to the non-trivial velocity fluctuation here, but once the U zero is large, this guy can create the instability. So therefore, this is a two-way interaction. You can find some steady solution which exactly satisfies this balance. So what is also known is that this particular nonlinear term here for the wave equation does not seem to be very large for many exact coherent states. And this is the well-known theory by Phil Hall and his early work in 1991 on compressible flow. He later extended to the Couette flow. And we did that with Bruno Card before he passed away. So basically, you can see that many exact coherent states do not have large contribution by this term. So what this means is that if you take out this term, this equation becomes linear. Therefore, there is no way to have a nonlinear transport in the streamwise direction. Therefore, there's no way to send the energy from the large streamwise wavelength to small streamwise wavelengths. So therefore, what is expected is that the exact coherent state will not have healthy energy cascade in the streamwise direction. So this is exactly what we see from the previous picture here. And the other thing that I like to say is that this one is also kind of triggering the energy cascade in the streamwise direction. Therefore, it's kind of acting as a precursor of turbulent dissipation. So which means if the Reynolds number is large enough, and this linear term, we try to do something, but this linear part of the equation typically give you the large value around the critical layer of the streaky value. These are the exact state that you see here is that these have all, these are dissipation, the blues are dissipation, they are all around the critical layer. And what is interesting is that you do see the same exactly in the turbulent flow. Okay, basically, this streak instability process is kicking turbulence dissipation. Okay, that was the one thing. The second thing is that let me come back to this picture. Okay, so we had the energy cascade here. And then what is happening is that we transport energy from large to small scale, but sometimes what is happening is that the transported fluctuation to small scale excite the production at small scale. Okay. But the production you typically requires actually V fluctuation to have non-zero value. So let me track what is happening here. So what I'm going to do here, I try to compute the correlation between this pressure transport and the nonlinear transport in Y direction, okay, and this the small scale production. So if you look at these three time trace of three observables, especially if you look at the black one and the production at small scale, you see that they are fairly well correlated. Okay. And then if you really calculate them, the correlation coefficient is not really small. It's 0.5. So let me see what is happening here. So let me just take the one instance here. This is again the time trace. And then this is the black one is the blue one is the pressure strain transport at large scale. And then the black one is the nonlinear transport, interscale transport. And the red one is production. And here is this yellow one actually presents the small scale streaky motion. So let me run a movie. You see that when the nonlinear transport become large here, you see that production and this nonlinear transport actually are all collocated. Okay, so basically this triggered the production like this. If you look at this picture from side, that's what we see here. I think quite many of you are familiar with this. This is the OR mechanism. Okay, this is not the intrascale process. This is the interscale process, essentially. So let me conclude. So my original question, the answer to the original question is probably not. And what exact coherent state really do is that they actually depict the partial physical process of the multiscale turbulence. So also we learned quite a lot by doing this. We have two large scale self-sustaining process, small scale self-sustaining process. And then the most fundamental thing is shear turbulence is the production and dissipation, and mean shear pumping the energy for the lift-up effect. And dissipation takes place when the streaks break down. In between, when this guy breaks down, it can trigger the OR mechanism, cause another dissipation. The other thing that we discovered, sometimes when waves break down, it can feed to the larger scale energy. And this is related to that particular type of the coherent state. And the last thing I like to say is that then we may get the criticism that we really didn't compute the right solutions. Okay, that's a true criticism we have to take. But then let me explain how difficult computing such a solution is. I'm going to consider two-scale system. So the shear flow, it has to have different speed. Therefore, if you consider two traveling wave speed with two traveling waves propagating with a different speed, then in the moving frame, this solution must be periodic orbit. So we tried to find this multi-scale periodic orbit by superposing many solutions, but we never been able to find that. But what this picture also say that if you begin to consider the dynamics of these two structures, it will be very exotic solution like quasi-periodic solutions such as the tori, etc. So in general, if you consider many scale, they should be quasi-periodic, very chaotic solution. Okay, so that's the general difficulty. But actually, we know that we increase the Reynolds number, it's getting incredibly difficult to calculate this kind of orbit. So let me finish here. Okay, so.
Here we go.
Yeah.
So thanks a lot. I just wanted to add to your last point is exactly what I wanted to say before. What if we have to look for tori and
yeah.
and then we are lost? So I wouldn't say the dynamical systems picture is wrong in any way, but we don't have the means to find the structures that are relevant.
Which is exactly correct. That the one point I wanted to raise here was that the ergodicity. So we can have a periodic orbit, but not all the periodic orbit are necessary to the contained interaction. If you just have periodic orbit for the same process each scale, we will see the same problem, right? So the question is, we do need to find a solution, periodic solution that really resembles fully everything in turbulent state. So that is computable or not is something else. But you're right. Actually, we should. But that's the point that I like to make. Yeah.
Okay.
I think there was. Okay. Yeah. So,
Like Tobias answering a question told us that bursts might be characteristics corresponding to the transition from one, say, periodic orbit to another. And what you just showed us, isn't this something similar with this OR mechanism? Can this be interpreted as this jump, the event where we go from one to another?
So that is possible. There might be some heteroclinic connections, if we were able to compute. I'm not saying that there is none, but given our computing capability, I don't know whether we can compute that, but I haven't really tried yet. But you're right, it is possible. But if you have this Reynolds number, computational period orbit is incredibly hard. So I don't know.
Okay, we have one in the back of the room here, then we have Predrag, and then Javier.
Thank you, Yongyun. I really enjoyed your talk, and I think you're framing this question about whether this subset is ergodic is a central question. But I'm just puzzled that instead it seems to me that it's not, as you show, and there are two that suggests two alternative paths, and it seems like you're taking one, which is to change the physics to match the lack of ergodicity that it's exposing. But the other take would be to change the statistics. We don't need to assume that the process is stationary and ergodic. And so, I think what that means is that when you look at your large scale structures, you have to confront the fact that in each realization of the flow, they're occurring with some random phase that can't be predicted. And so if you go back to just kind of a general ensemble average and think about that, then it would suggest a different, different statistics in your triple decomposition, and that could solve the problem too, right? Why do we have to change the physics to match the ergodic hypothesis?
I don't know. I cannot really answer to. I don't have a good answer to that question. But what I personally felt is that I think something different, something radically different approach is needed, right? So like you just said, okay. So that's what I feel at this point. But
the central fact is that you're saying that the small scale motion is modulated.
Yeah. Yes.
And if you assume that it's stationary and you break up the flow the way you do, then that tells you that they're not flow. It's by definition of averaging. you're imposing an onslaught that gives you something that's impossible. So you can change the onslaught rather than
You know, if this was a question, you'll have to repeat it because we didn't hear it online.
Oh,
Okay.
okay. Well, Predrag,
Yes,
stay online though, because we're going to have you talk. We're going to have you ask your
Yes,
question
I can.
next.
Yeah, we can change the answer, but the question is that the description.
Sorry,
Okay.
for those online, I shouted out that, you know, shouldn't we change the onslots rather than trying to change the physics? So the fact is that the small scales are correlated with the large scales. If you impose ergodicity, this can't be the case. And so you have to relax that rather than trying to make the physics fit the onslaught.
What do you mean onslaught? Actually, I didn't
The
understand.
onslaught's meaning that you've broken up the flow and you've assumed ergodicity in order to do the averaging, which leads to the balance.
Yes, so that
Which leads to the balance equations, which then lead to results that contradict the original hypothesis.
yes, that's right. So,
So if you go back to an ensemble average without ergodicity,
yep,
then you wouldn't have that necessarily have that.
that is
problem.
true. That is true. So that is true. So the point that I was trying to make to deliver is that we can't make that answer actually with this type of approach, and then we need some different type of approach, you know, so that to describe the dynamics.
Right. Well,
Okay.
I'm violently agreeing with you.
Yeah.
Is I think what's happening.
That's what I wanted to say. So that's my conclusion in a way. But actually, thank you for highlighting this. Actually, it's true. You're quite right about that.
Okay, Predrag, you're on.
So the first question is, you know, early work by Rich Kurzweil and many other people since, including us, is our experience is that relative equilibria and equilibria, which are exactly as structures in your language, they tend to be very far away from ergodic area of interest. And
Yeah.
one indication is their instability. So you didn't tell us, but are your solutions very unstable compared to instability of the flow, average instability of ergodic flow? Do you have some sense?
Yes, so they are very unstable. Typically, we get, you know, from 20 to 60 unstable eigen values for each state. So that is very true. And here, actually, I'm not talking about whether the periodic orbit or the equilibrium, the relevance of the equilibrium state or periodic orbit for this particular problem. Here, what I am talking about is that if the invariant solutions do not contain the multiscale physics, they are not actually useful for example, the cyclic expansion, for example. That's what I'm trying to talk about here.
And then I have just a remark, you know, which might be wild and doesn't work, but it hasn't been tried really by anybody in fluids. If you know the shape of kind of thing, you know, when you're in turbulent state, you see some recurrent shapes, the size of the things that you look at. You know, I'm suggesting in my talk yesterday that instead of doing time integration and trying to find periodic or toroidal or God knows what invariant solutions, try to guess the shape of it and use optimization problem to globally solve it without integrating in forward in time, but just ensuring that locally you set equations of motions. So there'll be a very different approach to how you would find these solutions.
Yeah,
You cannot find, you know, solutions that you cannot find. Same with us, we were totally unable, including Ashley Willis as a part of this collaboration and Mark Avila. You know, maybe you should try to find them in a very different way that you're looking for them right now.
Yes, so I definitely agree, but it just one thing I felt is given our computing technology we have that heavily depends on the Lyapunov exponent. As we already have a two-scale system, but the Lyapunov exponent is large enough for us to fail computational orbits. So my impression is that I don't know. So if someone come up with a much better technology, I think that would be one way to go. But the other way we are trying to go is try to come up with a low dimensional systems. In a way, this minimum flow unit is a low dimensional system of the white box. You remove the space from the dynamics and try to understand that in temporal dynamics. So in a similar fashion, one might come up with a reliable low dimensional model for vertiscale turbulence, and we try to compute the orbit. That's a kind of try to kind of answer what's going on in the state space. I'm not saying I know about the state space, but that there might really be some invariant solution that have everything. So just I can't compute at this point.
I just want to ask to this, I mean, to the invariant solution people here, whether anybody has checked the paper by my previous collaborator, Sekimoto. He claims to have a periodic orbit that has two scales.
Okay, I was not aware. Let me check.
I mean, somebody should do that. I mean, my name is in that paper for absolutely no reason, but I'm completely unable to judge it.
Okay.
All right.
I just had a very small question. Do you see any Reynolds number dependence in the failure of the minimum of the ECSs to reproduce turbulence? Is it more so as Reynolds number go? Is there a tiny range in Reynolds number where they might reproduce it at the low Reynolds number?
Yes,
say?
low Reynolds number whenever you have only one scale. So if you have energy cascade, I don't think you will get something. So the two scale system, you do have energy cascade, although it's very narrow. So then I begin to see the problem. Yeah.
I was going to close the session, but since Rich wants to continue, I'm going to keep. Yeah.
Just a small comment. I mean, I've made this comment before when you gave this talk. I don't see why you have the confidence to call this a multi-scale system. Your large scale is one wave number in the spanwise, the outer scale, and then you're drawing all these conclusions from just that, and then everything else. I mean, what's to say that you couldn't, cut your domain in half in terms of the spanwise wave numbers?
And that's what I did.
No, but in terms of the wave numbers, not the actual spatial scale. You just have KZ as your outer scale.
Yeah.
I'm saying, split the wave numbers in KZ. So I don't know how many you've got in your simulation, 30, 60, and the first 15 are your scale, but it's all quite artificial in some sense, right? Why do you consider
okay, so let me explain that to you. I think twice again.
Well, let's try again.
Yeah. So you see this here. You see that this strict structure elongated all the way down to the domain. So basically, at this scale, the largest energy containing wave number is a kz equal plus minus 1, first the fundamental harmonic, and the kx equal, say, 0, right? So basically, but in this one, you see the same, kz equal plus minus 2, but it has to contain everything in x direction because the smallest length scale is still extended all the way down to the box side. Okay, I'm not claiming that I did a very clean decomposition, right?
Isn't it just arbitrary?
Yeah, but I'm not claiming that I did that in a very clean way. But my point is that if you do so, then this one capture mostly large scale, that one capture mostly small scale. That's what I'm saying. I'm not saying anything more than that.
Yeah, but your projection operator forces that.
Projection operator is what?
P, yeah. P just takes the largest spanwise wave number.
Yeah, so there is a problem in a way that describing. I
mean, you could do this with any traveling wave. You could just say it's three
yes, that is
scales
possible. But
you could have two projection operators.
So for example, our small scale solution has 0 value in the UL.
UL, what's UL?
It's the largest scale velocity field. We don't have a large scale velocity field for, from small scale solutions.
And your small scale solutions are based on the fact that KZ is.
Yeah, we don't have any KZ, any energy.
All right, so this is a traveling wave in half the box.
Yeah.
And then what's the structure in the large box? Is that another traveling wave?
This is not half box. This is just in the large box. Okay.
Right.
we basically set the exact copy, 4 copies,
Right.
and then we continued in the y direction. So these
Right.
two are there at the same box.
So
So
they're
this
two-
one does not
ah.
have a UL.
So they're two different ECSs.
2 different ECS.
Right. I see. And then the other one only has KZ in the highest.
Yeah, so in this one, there's
Yeah.
no energy in the UL
I
component.
understand that. Yeah.
That one, the UL component, energy in the UL component is much larger than the US component.
Yeah, but it's still got structure in the lower.
Yes,
K-
I
in
do.
the hi-
This is the point that I'm saying. I agree with you,
Right.
but we have to have some decomposition to define the observable.
Yeah.
So that's not clean cut, as you said,
Yeah.
but it does the job reasonably well.
Okay, so the other comment I would have, if I'm allowed, Mr. Chairman, is that you're making the point based on the fact that these ECSs are fairly quasi-linear,
Yes.
and nobody expects quasi-linear waves to explain turbulence. You've got to move away from that, and you've got to track some instabilities away. So I know the VWI basically gives you quasi-linear approximation.
Yeah.
But for the reason that you just illustrated, you're not going to get that fluctuation interaction.
Sure, yeah.
So that's what you've highlighted today,
Yeah.
but nobody expects these quasi-linear waves to do the job. They're in the space, but all the connections between them and all the orbits, the more complicated things which branch off them, are the ones that are giving you the complex dynamics.
So I'm not saying the quadrilinear dynamics will describe the turbulence. Okay, there is a confusion. I'm saying the exact state that we computed seems to be well described by the quadrilinear description. Therefore, that particular term is lacking in the ECS.
Yeah,
right.
I agree.
That's what I'm saying.
Yeah, I agree.
Yeah.
You can't generalize.
No, I can't.
Yeah.
I can't. That I know. I'm just highlighting that is a missing piece in the exact coherent state.
Yongyun, I could have a question if I may,
Yes.
or maybe more a remark. I mean, there's what I would say a beautiful paper by Leonard Van Veen, Alberto Bellamartin, and Genta Kawahara.
Yes, I know that paper.
Well, they computed an exact periodic orbit which features all scales. It's turbulent. It has a spectrum like turbulence itself. So how does this fit with your arguments?
Okay, so number one, that's for the body forcing, the isotropic turbulence driven by body forcing, if I understand right?
Correct, but still multi-scale and periodic. And
multi-scale, but my point is that you can have the multi-scale solution in Rayleigh-Bernard convection too, that I know. So the point that I like to make is that that solution is the solution for, I believe, the energy cascade. But the solution that I computed here is for self-sustaining process, which does not have healthy energy cascade. So you see what I mean? That one by Genta is for energy cascade, which is a particular process in the flow, and self-sustaining process is another particular process of the flow. So that was my understanding, but of course, someone can compute the multi-scale solutions, but I'm just talking about this with the solution we have.
Excuse me.
Okay,
Sorry to interrupt.
Genta wanted to get in here.
Yeah, I'm Genta from Japan,
Yes.
and I think the shear is crucial thing maybe. If we would be free from the shear, for example, as Mark mentioned just before, and I'm also working on the thermal convection. At least I can say that in these two cases, we have multi-scale solution. They represent the turbulence dynamics as well as energy cascade process.
Yeah.
But I'm afraid I cannot have the invariant solution representing the multi-scale and wall shear flow. Maybe the shear should be important. Maybe, as you discussed before, maybe we would be going to the Tori and so on because we have shear.
Yep. This is exactly what I felt too. I have to agree with you about that.
I see.
Okay, I'm gonna bring this session to an end. I wanna thank everyone for an exceptionally engaging session. I think I've got my steps in today already. So, and let's all thank all the speakers. And Rich tells me we're going to take a full half-hour break and visit the posters during this break. So let's thank the speakers once again.